Ready?
Ok, entonces lo que Puyan es un estudiante de doctorado de acá de la universidad, de mi universidad, y ya la dio cuando di la última vez la clase, era mi jefe de trabajos prácticos, entonces también dio esta clase, pues tenía sentido que la dé de nuevo. Y lo que vamos a ver, y probablemente va a durar menos de 2 horas, pero vamos a ver análisis de Ouroboros, ¿sí? Un poco en detalle, ¿sí? Y para que tengan idea de la... También es un poco avanzado porque mm, eh, el análisis usa random walks, que no sé cómo se dice en castellano, ¿hay alguna traducción de random walks?
No, no me sale
Sí,
ninguna.
sí, pero lo interesante de esto es que es un random walk que va a suceder en el plano. Si uno puede ver lo que estuvimos sabiendo del análisis de Bitcoin, el Bitcoin Backbone, sí, es un random walk sobre la línea, ¿no? Uno tiene suerte, uno no tiene suerte, entonces puede trabajar, uno puede caracterizar como un random walk. Son pasos aleatorios, ¿no? Uno está tratando de caminar y en cada momento uno va para un lado o para otro, etcétera. La cuestión de Ouroboros que tuvieron que hacer para analizarlo es un random walk sobre el plano. Sí, vamos a ver hay distintos tipos de zonas, etcétera. Es un poco involucrado el análisis, pero les va a dar una idea de lo que tuvieron que hacer. Y en realidad el análisis de Ouroboros está basado, el propósito es demostrar las mismas propiedades que demostramos para el Bitcoin Backbone, como Common Prefix y todas esas propiedades, pero cuando el proceso de elección de quién va a ser responsable de un bloque, la elección no se hace por Proof of Work, sino por Proof of Stake. ¿Sí? Entonces, pues lo que va a hacer es va a empezar un poco de repaso de lo que hicimos en el pasado y va a salir con el análisis. ¿Ok? ¿Hay alguna pregunta sobre esto? All right, so Poyan.
Yeah.
So you're also, yeah, go slow. The idea is probably you're gonna do it in one shot without taking any breaks and stuff. All right, and what I just told them is that the analysis is a bit involved, but just try to get the most out of it, just to have an idea of what kind of things they do and so forth.
Yeah. Okay.
Okay, and all right, so take it away. Thanks, and I'm gonna bail out soon, but I'll stay here for the first few minutes. And so you're recording, right? So you're gonna get
Yes.
so you're gonna get the recording, and when you're done, you can just sign out. All right. Okay. Thanks. Take it away.
Thank you. Okay. Hello, everyone. Thank you for the introduction.
Sorry,
yes.
Puyan, one small thing. You have a dialog open in the bottom of the screen, which is saying apps. At least I see. Yes. Yeah. Thank you.
Thank you. So yeah, today we're gonna briefly recap what is proof of stake and the related background, and then we delve into a specific protocol named Ouroboros for proof of stake blockchain. We give the description of the protocol and a few other things that is necessary to be defined for the analysis, and then we go over the analysis, but at a very high level, because as it said, the analysis is kind of involved and complex. But we were trying to cover as much as we can here. Okay, so as we all know, Bitcoin has had challenges, and the question is this the best solution that we have under the same set of assumptions, namely this permissionless network distributed setting? And because we're mainly asking this because we know that Bitcoin is slow. To give a comparison, for example, Visa network can process 2,000 transactions per second. PayPal can do 100 transactions per second, but when it comes to Bitcoin, we only get about 15 transactions per second, which is like very slow, slower in order of magnitude. So it's a natural question is that if we can actually achieve a higher throughput under the same set of assumptions. The other issue is that Bitcoin is not very energy efficient. And in the more, if we want to be more specific, the Bitcoin network in 2020 consumed the same amount of energy as in Denmark as a whole country. So it's not very environmental friendly and it's not very energy efficient. So the other question is that can we adjust these assumptions or hypotheses that we're using, and by that we get a more efficient solution for maintaining a ledger in a distributed manner. So to better understand that, what components in Bitcoin that we can change is we need to take a look at Bitcoin structure and to see how it works at a very high level, and then to decide if we can replace some of the components or do things in other ways and make it more efficient. So generating a new block in Bitcoin is very similar to process of electing a leader. So parties preparing block, and then basically we in the Bitcoin we first elect the party in some way, and then that party proposes a new block and extend the blockchain. And this election in Bitcoin is based on solving a moderately hard problem, basically solving a puzzle, and who can solve that puzzle win the ticket to extend the blockchain. So since this puzzle is computationally difficult, the probability of being elected basically is proportional to your hashing power, to your computational power. And that's where actually Bitcoin is consuming the most energy to do this election process. And of course, solving this puzzle, maybe some honest parties can solve it simultaneously. So they want to extend chain at the same time. Naturally, it caused that we have some forks naturally emerging in the execution. And to reconcile that and to solve that and make a consistent view for everyone, there are some selection mechanism, chain selection mechanism. For example, the longest chain rule in Bitcoin provide a way for parties to decide which of these multiple branches, multiple histories of transactions they should consider. Basically, the longest one in Bitcoin is the one that we want to keep. So if we can replace this physical resource, this hashing power, with something else like a virtual resource, like the stake of parties, then we probably can get away with this high energy consumption and do it another way. So the main idea in proof of stake is to use this virtual resource. That could be your money that's already the ledger itself can maintain that virtual resource. So it's like, for example, as I said, it can be your money in the network or whatever else that you can record on the blockchain. And in a very high level, so you have these stakes, every party have a stake, and there's the stake distribution for everyone. And then you define a set of miners, basically a set of validators, parties that can generate new blocks and extend the blockchain. And those miners are the stakeholders, and their stakes is reported on the ledger. Everyone can check and verify. And then we have a randomized process that look at the stake of these miners, and with the probability proportional to their stake, elect those miners and allow them to extend the blockchain. So in some sense, everything is very similar to Bitcoin. As you can see, parties getting elected by some probability proportional to some resource, and then they get to extend the blockchain. But the resource here is not the hashing power anymore. It's like a virtual resource. So hopefully it helps us to get better performance than Bitcoin. So this is the general graph. As you can see, at the very extreme, we have these centralized databases like banks or these web servers. So they're decentralized. There's a single point of failure, but they are very efficient. There is no redundancy in the system. There is no indiscrepancies in the views that you need to fix and things like that. So it's very fast, very efficient, but it has a single point of failure. On the other extreme, we have Bitcoin. So there's a distributed network, permissionless, everyone can join, leave at their will. But maintaining a ledger there comes at the price. So we need to solve this proof of work. It's very energy inefficient and it's very slow. And we have some other approaches in between, like maintaining a ledger by sequentially running multiple Byzantine agreements protocols back to back. So it's definitely more efficient than Bitcoin, but it is not as decentralized because mainly for classical Byzantine agreement protocols, the set of participants need to be fixed. So it's not like a permissionless network. You can go join and leave whenever you want. So it's exactly, we can place it in between in terms of decentralization and the performance between these two extremes. But hopefully proof of stake blockchains can solve this problem. We get the same decentralization as Bitcoin because we want to design them in the same setting, the permissionless network. And potentially they can perform much better because instead of relying on that physical resource here, we mostly rely on those virtual resources that basically cost nothing. Generally, there are two major approaches in the proof of stake. The first one is proof of stake blockchains, which are essentially very similar to Bitcoin, the proof of stake notion that we were discussing till now are in this category. So you have a hash chain like Bitcoin, and then you have some sort of longest chain rule or things like that to help party decide which chain, if there are multiple of them, which chain they have to adopt and then extend that chain. A lot of protocols, including Ouroboros, Snow White, and others, following this idea. And there's another idea, is proof of stake, BFT, and BFT here stands for Byzantine fault tolerant. And the idea is to adopt this classical Byzantine fault tolerant protocol to operate in the proof of stake setting. So basically, validators propose the next block, and then parties go through a number of rounds of voting to decide which proposed block needs to be like which of those proposed block can be added at the end of the blockchain, or which of those proposed block can extend the existing blockchain. So a number of other commercial blockchains like Algorand follow this approach, and here there's always a single chain. There's no possibility of having multiple chains at the same time, because when new blocks are proposed, then parties gonna go through that voting mechanism and then agree on one of the proposal and append that to the existing chain. So we have like immediate finality for transaction in this setting. So, but both of these approaches are based on the proof of stake idea. So they're both categorized as the proof of stake protocols. So there was a folklore, essentially mainly between Bitcoiners. They thought that proof of stake blockchains won't work in the setting where Bitcoin works. And the reason for that was like two main observations that they had. The first one was costless simulation, essentially saying that the adversary, when winning a slot when winning the lottery, being elected, can invest in all the chains, all the transaction histories that are in existence, or even can create new ones, because generating a new block is costless. Once you're elected, there is no limit. You can generate as many blocks as you want and extend all the existing histories. But in Bitcoin and in proof of work blockchains, it's not like that, because the miners or the adversary needs to first commit to one of the chains, one of the transaction histories, and then solve the puzzle for that chain. And once the puzzle is solved, the adversary can only extend that specific chain. So if the adversary wants to invest in other chains, he needs to use a portion of its computational power for those chains. So it needs to split its power. It's not costless for the adversary to simulate and generates blocks for all the histories. But in the proof of stake, since the stake is valid in all the chains, the adversary can simply add multiple blocks in a single time it's been elected. The other name of this attack is nothing at stake attack, basically because there is no cost to that. And the other issue or observation was long-range attacks. So basically, imagine a situation where a new party is being joined to the network, or a party was offline for a while and now wants to rejoin to the network. And at that point, it may receive a number, maybe 2 alternative histories from the network. And there should be a way for that party to decide which of these 2 histories is the one that is valid, which one needs to be adopted by the party. This is a graphical illustration of that. For example, at this point here, the adversary who accumulated some stakes decides to generate 2 different blocks and create 2 chains in parallel, and then a parties that joining here cannot decide which of these 2 branches is from the honest parties. But it turns out that these 2 attacks can basically be mitigated by correct mechanism. And we'll see that, for example, Ouroboros, it has like a proof of security showing that these things cannot happen. Ouroboros follows kind of the same approach as Bitcoin, following that longest chain rule here to help this firstly joining party decide which of these 2 branches is valid. But the definition of longest chain here is kind of different, because in Bitcoin, the longest chain was the chain that has like most difficulty in it. But here, for example, we should define it as the chain that has like most block in it, for example, or more stake has been used in that. Yeah. Okay, so now we can go over the description of Ouroboros. As I said, Ouroboros is the first provably secure proof of stake Nakamoto style blockchain, and it introduced a basic design structure for building secure proof of stake blockchains. The design structure, this has 3 stages. We're going to see and discuss them. And they also introduce some notions that's helpful in the analysis of proof of stake protocols, like namely these characteristic strings, forks, and forkable strings. We're going to see all these notions, and we're going to use them in the security proof later on in this lecture. Say that how these ideas can be used and generalized to other proof of stake protocols as well. So the name Ouroboros coming from it's like a alchemical symbol. It's basically snake or dragon eating off its tail, form a circle, and it's a symbol of destruction and recreation. as we see the description of the Ouroboros protocol, it will become more clear why they choose this name for their construction. Okay, the design structure that we were talking about has 3 stages. Stage 1 is the static stage. So in this stage, we assume that the initial stakeholder distribution remains the same throughout the execution and forms basically a root of trust in the system. So it's not going to change. It's something hard-coded. For example, in the Genesis block, we have the stake distribution, and it's going to be this, remaining the same thing throughout the execution. Then we can refer to that as a point of trust. In the second stage, they use a trusted beacon, a randomness beacon, that emits randomness, basically seed at regular intervals throughout the execution. And then these seed can be used at the beginning of those intervals, and allows parties to kind of let the stakeholder distribution evolve through time. So you start with this distribution from the Genesis block, and you have a seed there. You continue the execution, and then you receive randomness from the beacon. Then you can look at the ledger itself, update the stakes based on the transactions happening there, and then use the new seed from the beacon, and based on that seed and the new updated distribution of the stakes, you elect the next leaders for the next blocks to extend the blockchain. And then again, after a number of blocks, in the beginning of the next interval, you can check the ledger again, update the shares, and then receive the seed from the randomness beacon. And using the seed and the new stake distribution, you can elect the remaining leaders and extend the blockchain and continue like that. But here we have this trusted beacon. It's a like trusted third party generating randomness for us. So it's not very realistic. So in the third stage, they try to simulate this beacon with cryptographic means. So they remove this trusted party and then try to simulate that to try to find a random seed by communicating with each other and like probably leveraging the ledger that they have currently. So now you can see that why the name Ouroboros makes sense, because you have this ledger, parties using that, and they communicate to each other, they generate randomness. Using that randomness and this updated share, they extend the ledger, and then they use that ledger again to generate new randomness, and then use that randomness again to continue. So basically, the protocol generating randomness and using its own randomness to continue, and then generate the randomness again and use that to continue. So you see this cycle of destruction and recursion. So that's why they named their protocol Ouroboros. But in this lecture, we mainly focus on the stage 1. So consider static stake setting, and we don't care about like the other complications coming with this trusted beacon, evolving stakes, or things like that. But these 3 stages are generally are very common in cryptographic protocol design. You start with a very simple and basic model with strong assumptions, which is very simple to think of. And you design your protocol first for that setting, and then you slowly try to make your model more realistic and potentially using a weaker assumption. And at the end, you try to get something that can be deployed in the real world with ease. But this is the steps that you have to take. You start with something simple and gradually make it more realistic and practical. So the model that we consider in this lecture is the same as the Bitcoin backbones. So we assume we have a synchronous network that time is divided into rounds, but here we call them slots, and assume that messages are sent through diffusion mechanism, and we assume that adversary is rushing, meaning that a message is sent in each round. But basically, it means that adversary can read messages that honest party send in each round, and then decide about its own messages. And the adversary can spoof messages, inject messages, reorder messages, basically control the communication in the network. And the leader election that we said that we need to extend the blockchain, here we assume that we have ideal functionality that does that for us. So that's a special leader election protocol. So it takes randomness, it look at the stakes of the miners or validators and elect each party with probability proportional to its stake. So we want this form of leader election to extend the blockchain. And for now, we assume that we have an ideal functionality that does it for us. But later, I think we're going to see that how we can instantiate that using VRFs or other cryptographic primitives. And finally, we assume that stakeholders are always online. So it means that we don't see situations where this leader election elects a party, but that party is offline, so we need to skip that slot. We don't see these situations here in the analysis and in this lecture. But in general, you have to consider that. Okay, this is how a simple execution of the Ouroboros simple protocol for static state looks like. So first, on the very left, you have the genesis block, which has a seed, which is the randomness needed to elect the leaders. And then you have the stake distribution of the miners or validators. And then using these stakes and the seed here and that ideal functionality for leader election, you can elect leader 1, leader 2, leader 3, up to leader R, up to where you want to go. And each party here is being elected with probability proportional to its stake. So you can see in some of the slots, a leader is elected, but there is no block available. It means that probably that a party is malicious and decides not to generate any block for that slot. And in other blocks, you can see that the leader gather a number of transactions and sign that transaction, and like Bitcoin, potentially link that to the previous block, and then append it to the already existing blockchain. So of course, in the case, so for example, in this slots that adversary can, the slots that's assigned to adversarially controlled parties, they can generate more than one block. Here, they decided to just not to generate any block, but alternatively, they can generate 2 or 3 blocks at the same time, essentially that cost less simulation that we talked about. So in that case, we're going to have multiple chains here. And to resolve that conflict, that many chain, here, as I said, we again decide based on longest chain rule. So honest parties basically adopt the chain that has the more the most number of blocks in it. So this looks very simple, and it turns out that it works, but the analysis of this is more, even for this very simple case, is more involved than Bitcoin, but we're gonna talk about that. But before going over the analysis, there are some notions that we need to define first that facilitate the argument, the security argument. First of all, for each execution, we can draw this rooted directed tree that starts from this genesis block labeled 0 and then continues, basically showing that in each slot which blocks are generated and how they're connected to the previous blocks. And these double circles means that the slot belongs to an honest party, and this single circle with like a gray background means that the slot belongs to the adversary. And for each execution like this, we can define a string, namely characteristic string, that has length equal to the height of this fork. And for each slot, if it has 0, it means that that slot belongs to honest party. And if it has 1, it means that that slot belongs to malicious parties. And if it's bottom, it means that that slot's not allocated to anyone. So each fork can have multiple paths. Originally, in the original paper, they call each of these paths a tine, but here we may use these two terms interchangeably, tine or path. We mean each of these branches in this fork. The delta parameter is the number of paths or tines in the fork. For example, the fork here has delta equal to 3. So let's see an example of execution that leads to this fork based on this characteristic string. So we start with the genesis block. By convention, we assume that genesis block is an honest block. Then at the next time slot, an honest party is elected, and that party generates this block here labeled 1 and append it to the genesis block. Next, here, an adversarially corrupted party is elected. So that party doesn't need to generate the block and choose a branch to add that block to. It can wait until the next honest party is elected and then decide which course of action is the best, is the most favorable for him or her. See, so here, after this honest party is being elected and generating this block, we have an adversarially, we have a slot allocated to a corrupted party. That party can wait until the next honest party is elected, then decide which course of action is the best. So here, this party is elected in this slot, and the adversary here decides to generate a block, but put it on a different path, put it on a different time from the genesis block, essentially making a fork here. And then the adversary, who's in control of network, can reorder messages and things like that, can first serve this path that is that ends with this block that is generated by the malicious party. Since this path and the other path has the equal length, but this corrupted path is served first, this honest party here will adopt the corrupted path. So these two paths have the equal length, so they both in the longest chain rule, they both are qualified, but since the corrupted one is delivered first, the honest party here will pick that. And then in the next slot, another malicious party is elected because we have 1 in the characteristic string. Here again, the adversary can wait until the next honest party is elected and then decide which course of action is the best. Here, the adversary decides to extend both of these chains. So it adds a block after this 5 here, and then add a block here after this 1. So basically extend both of these chains at the same time. So again, as you can see, this chain here below has length 3, but the chain in up there has length 4. But since the last block here is generated by the adversary itself, it can wait, not add it right now, serve these 2 chains to the honest parties, to the next honest parties that's been selected for the next slot, but serve the malicious path first. So make that honest party to select this lower path here. And then maybe after that, the adversary can add this block to the other other path on the above. So is it clear that how adversary can take advantage of the network and the selection rule to form this path? So we have enough time. Whenever you have questions or you feel that maybe extra explanation would be helpful, please don't hesitate, just ask, because we have enough time to cover everything we want. Okay.
Sorry, Pujan, I have one question. Sorry. Just, if this process can be just scale up, you can add an adversary can still add more blocks to fork even more chains of the in the system, or is any kind of limit to or limitation to that?
I see. So basically, when the adversary is elected in a slot, that slot is for adversary, and he can add as many blocks as it wishes to any of those existing history of transactions. For example, at this point here, when the adversary is elected, there are 2 existing paths, and the adversary can add a block to both of them. Even adversary can create another path and add the block to that. So there is no limitation on the number of blocks that adversary can generate each time it's elected. Because of that costless simulation, when you win the one of these slot, generating new blocks has no cost for you, because unlike Bitcoin, where for each of those blocks you need a proof of work, basically in Bitcoin, you need to first choose which of these paths you want to extend and commit to that, and then solve the puzzle for that specific path. And then when the puzzle is solved, you have a ticket for extending that specific path alone and not any other path. But here, once you're elected, you can generate as many blocks that you want and append to any path that you wish.
Thank you.
So yeah, so on so forth. The adversary can continue the execution, and each time that the adversary is elected, can wait to see what's coming up, and based on that, decide that if it needs to generate any block or which of these paths he wish to extend, and then does that, and then reorder messages and feed them to honest parties in a way that's most favorable for the adversary. So as we see, adversary here is in a much better position in the protocol execution compared to Bitcoin, because in Bitcoin, as I said, the adversary can only add one single block each time. And the other thing is that in Bitcoin, the adversary doesn't know who's the next winner, who's the person that can add the next block to the blockchain, because that follows from this proof of work. So parties trying to solve this moderately hard puzzle, and there is no way for the adversary to predict who's going to win. So every party has a probability of winning, and it's not clear beforehand. But here in the proof of stake, as we saw in the Genesis block, we have the seed, which is the randomness, and we have the distribution of the shares. And using this randomness and this distribution of the shares, you can calculate all the leaders, all the upcoming leaders. So everything you need to calculate them is already given in the Genesis block. So the adversary who can see this Genesis block can calculate all the upcoming leaders by himself. So it's another advantage that the adversary has here in this setting. And in addition to that, generating multiple different blocks for the same slot, that costless simulation that we talked about. And in addition to that, the adversary also can wait and act just before an honest party comes online. So there is no need to commit to a course of action, to set up actions soon. So adversary can wait, and exactly when an honest party comes online can decide which course of action is the best. So these things makes it more challenging to come up with a blockchain, with a proof of stake blockchain. Okay, so this characteristic string that we talked about, that W has 0 and 1, 0 for slots with honest leader and 1 for slots with corrupted leader. And so obviously this string is not known to participants in the protocol, but we, as person who is analyzing the protocol, we can consider that we can form that string and argue based on that we, on different situation, different pattern of election, leader election, what's going to happen in the protocol and things like that. So that's a tool only for analyzing. That's not an information that's given to participants. So based on that characteristic string, we can say that when the adversary can cause harm or when it cannot. Basically, for example, in a very simple sense, when the characteristic string is all zeros, it means that all the leaders are honest. So that string is not favorable for adversary, because in no slot an adversarially corrupted party is elected. So it's all honest parties, and they're going to follow the protocol. They're going to generate a single block, append it to the existing chain. So basically, our fork will have a single path. It will have a single chain, and the adversary cannot do anything about that. So that's not favorable. But there are situations, there are some strings that allow for adversary to create situations that's hard for honest parties, or maybe impossible for honest parties, to distinguish between different paths in the fork. So create a situation that the honest party cannot decide which path is the right path, is the correct path, is the path that's widely accepted by all honest parties, all the other honest parties. So to be more formal, if the characteristic strings allows for a fork, an execution that has two edge disjoint path of lengths equal to the height of the fork, then that fork is the fork that adversary looking for. Mainly because in that fork, the adversary can form two different paths, both of same length, and the length is equal to the height of the fork. So those two paths are the longest path in the fork, and both has this exactly equal length. So if we want to follow the longest chain rule to select among those two paths, we're going to be confused because both of two paths has equal lengths. So maybe if we go, the best we can do is to just pick them one by chance. So half of us will choose one of them, the other half will choose the other one. So basically, it's not possible to like reach a consensus. It's not possible to maintain this common prefix if we face these confusing situations, because the longest chain rule only works if there is a single longest one and everyone can choose that. So forks that allow for characteristic strings that allow for forks with two edge disjoint path of lengths equal to the height of the fork are the ones that adversary likes. For example, an example for such a string is 00110001 here. And why? Because we can think of an execution. Here we can see one example that leads to two paths of equal length that has length exactly equal to the height of the fork. For example, here the first two slot belongs to honest parties, so they add these two. They add two blocks, 1 and 2 here. Then the two upcoming blocks belongs to adversary, so they're from cont'd parties. So the adversary can append. The adversary can generate blocks for two blocks each time it's been elected, and with one of them generate a new path, and with the other one extend the existing path. But the adversary here can first generate the block on the new path and make the length of that path equal to the honestly generated path that we had before. Both here, we have up to this point, up to where the adversary is elected, the honest path has length 2. And then when the adversary is elected, in the next two slots, the adversary can add two blocks to this new path, making the length of that path equal to 2. And then before adding these two other upper blocks, serves this path below to the next party who's honest, next leader who's honest first. So that party will adopt this lower path, which is the corrupted path, and start working on that and extending that. And then that will become the longest path. The next leader who's been elected will select that lower path and extend that. And then once the last honest party here is elected, the adversary can go back and generates two blocks for that slot that he's been elected in, and extend the upper path here. So at this point, both of these two paths has exactly the same length. although the adversary adds these two new blocks here later in the protocol, not at the same time that he generated these two blocks in the path below. So since these two have exactly the same length, by serving the upper path first to the honest party, the honest party will extend that one. So as you can see here, the upper path has length 5, not including the genesis block, and the lower path here has length 4. But the last slot belongs to adversary. It has a 1 here. So the adversary can freely add a new block to the lower path and make the length of that 5 essentially equal to the upper path and equal to the height of this fork. So for this specific characteristic string, there is an execution and there is an adversary strategy that leads to this fork with two disjoint paths of same length that equals to the height of the tree. It means that based on this definition, it means that this characteristic string is a forkable string, which is a favorable string for adversary. So we call this string forkable strings. And the main goal is to show that in an execution of Ouroboros, the density of these forkable strings is negligible. So the situations in which the adversary can confuse honest parties happens with negligible probability. Okay, is it clear up to here?
For me, yes.
Okay. Okay, so as I said, now the main goal is to find the probability of these forkable strings. And ultimately, we want to show that that probability is negligible. But to be able to calculate that probability, we first need to define some variables and some extra notions that help us argue about that probability. The first thing we want to define is this parameter gap. For a fork that has like multiple paths, the gap for a path, for example here, the gap for this specific path T, the upper path here, is the length difference with the deepest honest node. What does it mean? It means that, so here first, without a loss of generality, we can only consider forks that ends with honestly generated blocks. And that why? Because the adversary always can come back and add blocks in the position that he was elected before. So we only consider the case that forks ends with honest block. It's not that important, but it simplifies the argument. So in that case, if you take the difference of length of the path that you are in and the longest path, then you get the gap for that. For example, here, the upper path here has length, including the genesis block, has length 3, and the lower path here, the longest path here, including genesis block, has 1, 2, 3, 4, 5, 6, 7. So 7 minus 3 is 4. So that's the gap, which means that how many blocks is behind is the path that you're considering. So that's the gap. Then we have reserve. It means the number of adversarial slots after the end of that path. For example, here for this upper path T, we have 1, 2, and 3 adversarial block after that. So that would be the reserve for path T. And then the reach for each path is reserve minus gap. So here, as we saw this, the gap for the upper path was 4, the reserve was 3, so the reach would be 3 minus 4 is minus 1. Intuitively, reach is the ability of the adversary to make that shorter path to get to the longer path. So here, this shorter path is 4 blocks behind of this longer path. And there are only 3 adversarially slots after that point. So adversary can at most extend this upper path by 3 blocks. So even by doing that, the adversary will be 1 block behind the longest path. So the reach of this upper path is minus 1. So it means that it can it will never reach the longest path. It will always be like at most 1 block behind. So this is the intuition behind this reach. So the reach for the middle path here would be 0 because that's the longest path, and the adversary can always make this path as long as itself. So it's 0. And basically, then there is no adversarial node after that, so the adversary cannot extend it more. So the gap here is 0, and the reserve is 0, so the reach is 0. And for the third path here, as you can see, the length of the path is 4, but the length of the longest path was 7, so the gap will be 3, but there are only 2 adversarial slots after at the end of this path, so 2 minus 3 will be minus 1. It also means that the adversary cannot extend this lower path to be of the same length of this longest path. So what does it mean? It means that in this fork, the adversary cannot do anything to confuse parties, because the reach of these two paths, these two shorter paths, are minus 1. It means that there is no way that the adversary can use those adversarial slots and extend those 2 paths and make them equal in length to the longest path. So the longest chain rule here will always select the middle path here. So that was for fork. And those parameters we define for a path, for each path we define them. And then for a fork, if you get the maximum of the reach of all for all the paths, that would be the reach of the fork. For example, here we have reach minus 1, 0, and minus 1. So the reach for this fork will be 0. That's the maximum for all the paths. And the margin for a fork is the second best disjoint reach. So here, the second maximum is minus 1. So for this specific fork, reach is 0 and margin is minus 1. Then for a characteristic string, so for a characteristic string, depending on how the execution goes and how's the behavior of the adversary, we may have multiple forks. And among those forks, we look, and the maximum reach for among all the forks will be the row of that string. That's the function of that string. We define it this way. So row of characteristic string W is the
Let's go.
So yeah, for each string, as I said, we have multiple forks depending on the execution and the behavior of adversary. And if we look at all those forks, the maximum of the reach among those forks will be rho of W, and the maximum of the margin would be the mu of the W. And then we have a theorem stating that string W is forkable, meaning that the adversary can win, if and only if mu of W is greater than equal to 0. So whenever the reach is not negative, the string is forkable. And why this is true, we mainly first consider one direction. Assume that the string is forkable, and then we show that the mu should be non-negative. So if the string is forkable, it means that there is a fork with two paths, t and t prime, where both has the same length, and they have the length equal to the height of the fork. And then consider another fork, f prime, in which we remove all the adversarial vertices after the last honest vertex on each of those two paths in F. And here, the prefix of t and t prime in F prime must have reserved no less than the gap. Why? Because we only remove the adversarial block at the end, and those two paths had the same length and was the longest one. So now, whatever the gap is, we are sure that we have more than that number of we have adversarial slots in the execution, so we can always fill those with adversarial blocks and reach to the longest path and even go beyond that. So the margin would be non-negative. And on the other hand, when the margin is non-negative, it means that there is a path other than the longest one that has a sufficient number of adversarial slots after the end of that can be extended to be at least the same length of the longest path in that fork. So again, that means that that string is forkable because we constructed a fork for that string that has two paths of equal length and both of the longest length in the fork. So that goal of us that was to show that the density of these forkable strings is negligible can now be translated to the goal to show that the mu
Yeah, let's go.
Okay, so as I said, our goal now is to show that the density of the strings with this mu with negative mu is negligible, because this theorem says that a string is forkable if and only if the mu is not negative. Oh, sorry, I think I said it in the wrong way first time. So let me repeat it again. So first, our main goal was to show that the density of forkable strings is negligible. And by this theorem, we know that a string is forkable if and only if mu is not negative. So now we, instead of showing that, we can show that the probability of mu being not negative is negligible. And that's what we're going to pursue from now on in this lecture. So based on the definition of rho and mu, we can form a recursive formula. And it's not difficult to see why that's the case. We just need to go over the different cases, like case by case, and see why it's true. But at a very high level, for example, when you add a 1 at the end of the string, it means that you're adding an adversarial slot at the end. So that means that you increase the reserve for each of the paths by 1. So technically, it increases the reach and margin both by 1. So as you can see here, when we added the 1 at the end, the recursive formula says that both rho and mu is going to be increased by 1. But when you add 0, meaning you add an unslot at the end, it's going to be a bit more complex. It's not like, because in the other case, we're going up diagonally. But here, it's not, it doesn't follow the same similar simple rule. Basically, if mu is 0 and rho is positive, when you add 0 at the end of the characteristic string, the mu stays at 0, but the rho decrements by 1. So basically, the adversary can compensate decreasing in mu by instead decreasing in rho. Because as we saw, this mu, the smaller mu is more desirable for us. Bigger mu, positive or 0 mu, is desirable for adversary, because greater than or equal to mu greater than or equal to 0 means forkable string, and in which the adversary can win. So here, by adding 0 at the end, the adversary can make the mu remains at 0 and only decrements the rho. But when the rho reaches 0, it cannot go negative, because reach cannot go, maximum reach cannot be negative. So it's gonna be at stays at 0, and then mu starts to going down. And in any other case, you're gonna go diagonally to the exactly opposite direction, and in the case we added 1. Okay. So these are the recursive formulas we have for this rho and mu, based on the single bits that we're going to add at the end of the characteristic string. As you can see, these recursive formula forms a 2-dimensional random walk, because these 0 and 1s going to be added at the end of the strings, each with a probability. 0 is the probability of electing an honest leader. 1 is the probability of electing a malicious leader. Those two happens with each with a probability, and each of them translates in an increment or decrement in one or two of these rho and mu. So basically forming a two-dimensional random walk. And this random walk is a very useful tool in analyzing blockchains in general. For example, even in Bitcoin, at the core of the analysis, we have a one-dimensional random walk. And the intuition behind that is that in Bitcoin, we define a uniquely successful round in which exactly one single party is winning the proof of work. And it can be shown that in those uniquely successful rounds, that block will be adopted by all the other honest parties if and only if the adversary cannot win the proof of work at that same time. So so what we would like is to have this uniquely successful round without the adversary also winning the puzzle at that round. So the probability of an honest party winning the proof of work is alpha. So the probability of exactly one honest party winning the proof of work would be approximately alpha minus alpha squared. And if the probability of the adversary winning the proof of work being beta, then we can form a random walk. And with probability beta, we walk upward. With probability gamma, we walk downward. And then in this situation, if we can manage to make gamma be greater than beta, this random walk will be biased and will going downward, which is desirable for us, because it means that as we go down, it means that the number of uniquely successful rounds getting bigger, and the number of rounds that the adversary wins the puzzle gets smaller. So at some point when we go toward negative, it means that there are a number of uniquely successful rounds without the adversary winning the puzzle. So, and in general, we can divide this line into three regions. The one region would be the high numbers. We call it hot region, and the other region would be the small negative numbers. We call it cold region, and the region in between, we call it volatile. And the goal is to show that this random walk moves toward cold area and will stay there. That's the main idea. So we want to do the same thing here for Ouroboros, for this two-dimensional random walk. So we're gonna draw this two-dimensional space and then show that how these random walks will move on that domain, and then divide that domain into hot, volatile, and cold, and then argue that by choosing appropriate parameters, we can make sure that the random walks will move toward the cold region and will stay there. So we follow the same idea. But as I said, it will be more difficult in the proof of stake setting because, well, for example, one of the reasons is that unlike the proof of work, winning a slot for the honest parties, even uniquely, does not necessarily constitute a favorable step. Why? Because when the adversary is elected, the adversary can generate multiple blocks, more than one blocks. But in the proof of work, the adversary could only generate one single block. And this difference make it difficult because we have a counting argument in Bitcoin that relies on the fact that the adversary can generate a single block each time. But here that the adversary may generate more than one block, we cannot use the same counting argument. But, and the reason for that is this costless simulation or nothing at stake attack that we discussed before. But the good thing is that it doesn't mean that we cannot prove security, but it means that we need to go through a more involved and complex analysis to be able to show that even in this scenario, we still get security at it. So based on the relations that we saw for rho and mu, we can see that this random walk, we have this 2D random walk. When we are in when reach and margin, when margin is positive, and reach is positive, the random walk forms a simple one-dimensional random walk in the diagonal direction, like going up this way and going down this way with probability gamma and beta. But when the margin reaches to 0, instead of continuing going down this way, it's stick on the margin 0 and only decrements the reach. So this is how the adversary can compensate and avoid going down in to negative margins. And negative margins is where we want to be, but the adversary doesn't like. So the adversary can, to some extent, can try to stay in the this upper part of this plane. But when the margin, when the reaches 0, then margin starts to decrement by 1 and going down in this direction. But then for coming up, again, it follows this diagonal direction. So as you can see, it's a random walk, but it's not a simple one-dimensional random walk. In certain areas of this plane, it forms a simple one-dimensional, but in general, it have a more complex behavior to it. So it makes it more difficult to analyze, but it's not impossible. So, and one thing, margin was the second largest reach. So margin is always less than or equal to reach. So the random walk never can go into this gray area here. So we have this part of the plane to work on. But what is the favorable step here? Where do we want to go? Which direction we want to go here? For that, let's first, we need to first define some regions, hot, volatile, cold, and then try to go toward the cold. But before that, let's define some other variables first that we're gonna need to make our argument, and then we're gonna define, as we need these variables to define those areas, hot, volatile, and cold. So the main goal was is to show that and so consider this, consider W has length, assume that W has length n, this is a string here, divide it, partition it into the square root of n substring, W in parenthesis 1, W parenthesis 2, to W in parenthesis square root of n. Each of these substring has length square root of n. Then define R sub t, where t is in the parentheses, be row of the first t substring here, and define m of t, where t is in parentheses, to be the mu of the first t substrings. And of course, when you don't have the parentheses, when you have only t, you mean that the row of the strings from W1 to WT, which each of these are bits, like the first up to the bit in the teeth position, and the same for M. And of course, you have a simple relation between R with like this index in parentheses and the R without that parenthesis. I know it's a bit annoying, this notation, but it was used in the original paper, so we wanted to follow that. In case you want to refer to the paper, it would be easier for you to understand, to connect these things. But so this is the way they define that. And as we saw in that theorem, now this probability of W being forkable can be translated to probability of Mn being greater than or equal to 0. Because M is the mu, and mu was that margin, basically, that we saw in the theorem. Okay, so as you recall, we have this recursive formula for reach and margin, and we saw that how it works on the plane. And using those same recursive formula, we can extract some facts about these parameters RT and RM, those two things that we defined. The first thing is that when the RT is greater than 0, it forms a simple one-dimensional random walk. Whenever we receive 0 at the end of the string, the RT gonna be increment by 1, and in the other case, it's gonna decrement by 1. So it's a simple one-dimensional random walk for RT when RT is greater than 0. And empty, again, if is negative, it also forms a simple one-dimensional random walk. And when RT is equal to 0, it behaves kind of differently. So when it's 0 and we receive 0, it's gonna stays at 0. But if we receive 1, it's gonna be increment by 1. And then RT will be positive and will be here, and then we have this one-dimensional random walk. And then based on this RT and MT, now we can define those three regions, that volatile, cold, and hot. So when RT is greater than a certain value, delta square root n, and MT is greater than negative delta square root n, for example, we call it hot. This index T here refers to this index for this MT and RT, because we parameterize it with this T, that which sub string that we're looking at. So we have this corresponding T for the hot, volatile, and cold here. So we have the same kind of similar inequalities for volatile and something for cold. Basically, as you can see, in cold, we are stating that M, when M is less than or equal to a negative number minus delta square root of n, and as we know, this M corresponds to mu, and we know that when mu is negative, or when mu is negative, when mu is negative, the string is not forkable. So that's a desirable event for us. So we want to show that this random walk starts initially from the volatile state, and it moves toward cold, and it's going to stay in cold forever with overwhelming probability. So it means that the execution starts and mu gets negative and going to stay negative for the rest of the execution, meaning that we're never going to see any forkable strings. At least the probability of seeing that would be negligible. So that's the main goal. So graphically, this would be our regions. Those inequalities will translate into these regions. So this orange part is hot, green part is volatile, and blue part is cold. And we start in the volatile and we want to show that we go to cold and we'll stay there. So now the favorable step is more clear. So we want to move toward this cold area. What we show here is basically show that probability of being at cold and staying there is overwhelming. Probability of being in volatile but moving to cold is constant, and probability of being in volatile and moving to hot is negligible. So we start from volatile with constant probability, we go to cold and we're gonna stay there. And we're never gonna go, or only with negligible probability, we're gonna go to hot. So this would be the diagram that we're looking for. And eventually it leads us to this cold and makes us stay there. So why the first one? Why when we are in cold, we're gonna stay in cold? So when we are in cold, it means that M is negative. And we saw that when M is negative, M acts like a simple one-dimensional random walk when it's in negative. So making argument about that is very easy. There are a number of theorems in probability that analyze the behavior of one-dimensional walks. So we can use those theorems, like we have this gambler's ruin, basically saying that when you're playing in a game with negative expected value, regardless of your strategy, you're gonna eventually go broke. So here, since the probability of the desirable event where an honest party is elected when we have a 0 being added to the characteristic string is greater than a 1 or a 1 being added or adversary being elected, because we assume that here we have the majority of stake being controlled by honest parties. So, and we elect parties based on with probability proportional to their stake. So the probability of electing an honest party is always greater than electing a malicious party. So it's a like negative expected value game for the adversary. So as we play, the adversary will go more broke. And we can formalize this like in a more in a mathematical sense. You can define this family of independent random variables Zi that can take values plus or minus 1, and plus 1 with probability 1 minus epsilon over 2, and minus 1 with probability 1 plus epsilon over 2. So the probability of being minus is greater here. And then the sum of the first t random variable, we call it yt, it's gonna have a tendency to go toward negative here. And we, in some sense, we have this constant escape probability stating that with constant probability depending only on epsilon, this yt never move toward 1, never get values more than 0 with constant probability. Or in more general sense, for each value k greater than 0, the probability of that yt ever reaching to this k will be this constant to the power of this k here. Okay, for now ignore this my annotations on the screen. So using using these facts about one-dimensional random walks, we can sketch a proof, but more details is available on the original paper. But at a very high level, we're saying that when mt is less than minus delta square root of n, the probability of at any time in the future ms ever climbs up to -1 is negligible, is less than 2 to the minus omega square root of n. And since, as you remember, we divided the string into a square root of n substrings, so there are at most that many times that this event could happen. So if that put all these things together, you'll see that the probability of being in cold and staying in cold is overwhelming. 1 minus negligible. And what remains is to show that when we are in volatile, we go to cold with constant probability and we go to hot with negligible probability. And for that, we can use this Chernoff bound, which basically saying that in a biased random walk, after a certain number of steps, t-step, we are gonna be tightly concentrated around the expected value. Basically meaning that the probability of that random variable y being greater than half of that expected value is negligible in the number of steps. So you can use this fact or use the other one, that gambler ruin, that constant escape probability, to show that when you are in volatile, you'll never, or with over, yeah, the probability of ever going to hot is negligible. And then you can argue that when you are in volatile, again using this Chernoff bound, you can show that when you are in volatile, the probability of staying there forever is negligible. So you have to move out. But we show that probability of moving out and moving toward hot is also negligible. And if you put all those things together, you can deduce that probability of moving from volatile to cold is constant. So basically, that's all we wanted to show. So we start from volatile. With probability, with only negligible probability, we may go to hot. With constant probability, we go to cold, and when we go to cold, we're gonna stay there. So that means that when we start, that mu gonna get negative and gonna be negative for the execution, meaning that the adversary cannot win in making those competing paths and convincing parties to select the wrong path. And this is that probability of workability for different parameters and different probability. This is here. These are the probability of electing an adversarial party. It depends on the stake that the adversary has in the network. You see that by reducing that slightly, being a bit far from half, which is like 50-50 situation, this probability of workability decreases in a very high rate. And so by choosing, by waiting enough time, this n is the length of that characteristic string, which is the length of the execution. If you have sufficiently large execution and with appropriate probability, you see that the probability of workability is almost 0. So there is no hope for the adversary to win. So with this analysis, we established this common prefix property of the blockchain. But for proof of stake blockchains, similar to proof of work blockchains, we can define these 3 properties. One is common prefix, meaning that common prefix with parameter k, meaning that for 2 chains, C1 and C2, adopted by 2 honest parties at the onset of 2 slots, SL1 and SL2, where SL1 is smaller. Then by pruning k last block from C1, that new pruned chain will be a prefix of the other chain C2. And then we have honest chain growth with parameter tau and s, meaning that consider the chain C adopted by an honest party and let SL be the slot associated with the last block of C, and let SL1 be a prior slot in which C has an honestly generated block. Then if the difference of these two is SL2 minus SL1 is greater than S, then the number of blocks appearing in that chain after SL1 is at least tau times S. And we also have this existential chain quality with parameter S. It means that when you have a chain adopted by an honest party, and in any portion of that chain spanning S slots, then at least one honestly generated block appears in that portion. So these give meaning to the ledger that we are making with this proof of stake protocol. And this is the original paper that you can refer to if you want to get more details about the proof, and you see the other stages of the design. And thank you very much.
Thank you, Puyan. Very nice presentation. Any questions from the audience?
Yeah.
Our large audience? Yeah, I found really interesting this kind of demonstration how to link the string wall to the probability wall in crypto. It's nice. I think it's here. I think in the chat there is a question from Thomas. Do you have access to the chat?
Yes, I'm reading that. Oh yeah, it's asking that is it not necessary to consider the case in which we are already in hot region? The answer is no, mainly because when we start the protocol, when we first start from the genesis block, we start from the volatile. So the protocol always starts from the volatile as the initial state. So it's sufficient to only consider consider the case starting from there. But even though if we want to consider being in hot, even that, I think since the random walk has a negative bias, I expect that we eventually get out of that hot and again go to the cold and stay there. But I don't know, there is no analysis for that in the paper, and it's not necessary. But yeah, it's a good question. Okay.
Okay. I think you answer the question. So, any other? No? Well, I stop recording now.